Hello, everybody. In this lesson, we're going to be going over motion problems again with our parametric and vector value functions. Interesting thing with being able to do motion on a curve versus our straight line motion is, if we remember, with our straight line motion, we talked about an object that was just going back and forth, horizontally, or back and forth vertically. And we're able to do quite a bit of stuff with that, but that's not totally realistic. Things do not just go in straight lines. We're going to have some object that's going to go, like a projectile on a curve. It's not going to go in a straight line. We throw an object that's not going to be, it's not going to go straight across to the person. It goes in an arc. Or, we might have something that does a lot of different things. It's more realistic to be able to look at motion within multiple parameters instead of just one, either x going left to right or just y. So instead, now we're going to have our motion, if we think of it as a vector, is going to have both our horizontal component with the x of t and a vertical component with the y of t going on at the same time. And as the motion changes, as we can see, the x and y components are not going to stay the same. They're going to change. And so therefore we're going to have our derivatives and our been able to look at all those different things that we normally look at, but with the both horizontal and vertical components. So in this table, I've compared all our straight line motion that we know with parametric, the way it would be with motion on a curve with parametric or vector value functions. So we have our position vector. Normally we would just be given as x of t or y of t. Well, here we will have the vector r of t, or a lot of times it could be s of t equal to, and with more parametric form instead of the vector value would be another way that it could be written with the s of t. Velocity is going to be the derivative of our position, which is the same thing here. Velocity vector is the derivative of our position vector. Acceleration, second derivative of the position, first derivative of the velocity, and again, same thing going on here. So all of that relates back and forth. It's the same thing, but now we just have both components that we're looking at. Speed, something that we didn't deal with heavily with our straight line motion. But speed is the absolute value of velocity. So then when we get into vectors, it's going to be the magnitude of our vector. And so remember, magnitude is the length or the distance of the vector. And so therefore, that's going to be in this form, which again is that position or distance formula, Pythagorean theorem, however you want to think about. But that's how we find the magnitude of our vector of the velocity. Remember, we want to think about that. It is of the velocity function. Displacement is, well, just our standard definite integral of velocity, and it's the same thing here, but again, we just have to do it. If we're taking the displacement, then we just have to split it between both our x and y components. New position, we had where we did the new position, so it's always a to b, so it would be x of b equals x of a plus our displacement. It's the same thing here, just vector r of b equals vector r of a plus the displacement with our velocity vector. So again, pretty much exactly the same. We're just now doing it with our velocity. Okay. So again, this one actually could be written in a long, more extended way would be like the x of a comma x or y of a got to b plus, and again that would be the whole integral of a to b of our velocity vector of actually that's right in there, so it would be x prime of t dt and the integral from a to b of y prime of t dt, and it can be expanded with the vectors, which we'll have to do later on. And then total distance is the we saw it more with this here, where it was the integral from a to b of our absolute value. That's, remember, our total distance, not the displacement, but the total distance. Well, if we think the absolute value is, as we set up here, is the speed, then that would be the integral of the speed, which we already know. Well, then that is exactly what we have here. Our total distance is the integral from a to b of the speed, but the speed is our magnitude, and if we were to put that in, what our magnitude is here, that'd be the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. And hopefully that looks familiar because it is our arc length. All right, so everything just relates back and forth. If you can remember straight line motion, it carries pretty easily into our motion on a curve. One thing to note, motion on a curve may also be presented as parametric equations, not just vector value functions. All right, so let's go ahead and get into this one here. It's a calculator allowed problem, so I'm going to go ahead and have my calculator ready to go here. We can go ahead, there we go. All right, clear that out. So we have for time greater than 0, which makes sense, the position of a particle moving in the xy plane is given by the parametric equations x of t comma y of t. For t is greater than 0, we're given our dy dt, and actually that's probably should be dx dt, looking at that now, because they both say dy dt. We need one of them dx dt. And I assume just going in order, this one should be the dx dt, and then dy dt. So we want to find the acceleration vector of the particle. Well, we're given actually our velocity vector right there. So our velocity vector would be exactly what I have here, because remember, our velocity vector right here is the two derivatives of our position. So that'd be 5t squared plus 3, 5t squared plus 3, comma, and then t sine of 1.2t. So if that is my velocity, then our acceleration vector, which is the derivative of that, should be 10t, comma, and then this one is going to have to be a nice product rule here. So that is going to be, let's do t times, and then the derivative of this, so that should be cosine of 1.2t times 1.2 plus, and then the derivative of t is just 1, so that would just be plus sine 1.2t. So that should be my acceleration vector. All right, so it says that we want to find the speed of the particle at time t equals 2.5. So remember, speed is our magnitude of the velocity. So speed is the magnitude of our velocity, which would be the square root of all, it is x prime of t squared, which this is x prime here, and this is y prime here. So I can go ahead and just say, well, that'd be 5t squared plus 3 squared plus t sine of 1.2t squared there. So if I want to go ahead and find the speed at t equals 2.5, I would just need to then plug 2.5 into our magnitude equation. So go ahead and plug that into the calculator here, and we'll get our answer. So that should be 5 times 2.5, right? 2.5, that is squared, plus 3. Now that gets squared. All right, so 5t squared plus 3 squared. All right, plus, and then I'm going to have 2.5 times sine of 1.2 times 2.5, close the sine. Oh, I already had a parentheses there, so I'm going to have to close that. It's going to fully close my sine. And then that should close that one out, and then that gets squared. Let's just make sure I typed all that in correctly. Hopefully I did. I don't know why that keeps moving on me. All right, so that was there. Close out the sine, and that should be good, right? I think so. So equal that out, and we get our velocity of 34.252. And that's going to be our speed. All right, so now we need to go ahead and find our displacement. So let's see, our displacement is just the from 1 to 3, right? And so then that would be the integral from 1 to 3 of our velocity vector. Remember, not the absolute value here, because we're not doing the total distance, which, remember, total distance would be the arc length, but just that. So then that would be the integral from 1 to 3 of our two derivatives here. So that would be 5t squared plus 3 dt, comma, integral from 1 to 3 of t sine of 1.2t dt, and be able to close that out. So go ahead and throw that into our calculator. So let's see, integral from 1 to 3, 5t squared plus 3. I'm still in parametric, so that has a t there. I'm going to go ahead and just change this back to function. Make that an x. So just make sure everything should work with the t in there, but I just want to make sure. So that would be 49.333. And then we'll go ahead and do the other one. Check my bone, make sure I'm in radians. All right, 1, 2, 3 of t sine of 0.2x, close that out. It's there, and then dx. All right, so that is 1.589, and that would be our displacement vector. Okay, and then we have our at t equals 1, the particle is at position -10, 3. Find the position of the particle at t equals 3. So this is one of our new position, right, that we have here. So we're going to go ahead and use that down here. So we're going to have our new position, which is going to be at 3. So that's going to be r of 3 would equal the old position, r of 1, plus really our displacement. So that'd be the integral from 1 to 3 of our velocity. So that is equal to r of 1 is the point -10, 3, and that is plus our displacement vector that we got, 49.333. I'm actually going to go back, since this is written as a point and we're talking about an actual point, I'm going to go ahead and write this as -10, 3 there, and then plus the that displacement that we have, 0.589. So then that would be equal to the new position of, let's see, 39.333, 4.589. So we just add up the x components get added up, and then the y components get added up. And there's actually going to be, I've seen it in numerous places when they have questions like this on an FRQ, they many times won't even ask for both positions. They'll just say, what is the new horizontal position of this particle? And then they'll give the information that you need. So that is interesting to take a note of. All right, so we have the next one here. For time is greater than 0, the position of a particle moving in the xy plane is given by the vector given here. We'll see sum is actually cut off to the next row, which would have liked to have not happened, but it is what it is. Find the total distance traveled. So remember, our total distance is actually, in this case, going to be our arc length. So that's going to be the total distance. It's going to be the integral from 1 to 3. And in this case, let's see, this is our position vector, right? Position vector. And so this is going to have to be the magnitude of our velocity vector. And so we're going to need to know our velocity vector. So v of t is equal to, that should be 8t plus 5et. 5e to the t, comma, 6t squared minus 7 cosine of t. All right, so then when I put this into my equation, it's going to be actually turns into our arc length. So we're going to have 8t plus 5t e to the t squared plus, next one, 6t squared minus 7 cosine t squared and dt. All right, and so then that is running out of room a little bit, but we can go ahead and throw that into our calculator and see what we get. So 1, 2, 3, and then that's going to be the square root, and we'll have 8t plus 5t e to the t, and then, as forgot, need to square that, plus 6t squared minus 7 cosine of t. Close out the cosine, close out that, and square that, and then we should be good to integrate. So there we go. That is our total distance, or arc length, for that position or particle. All right. Okay, so we have one more here. This is a problem from the 2016 BCFRQ number 2. And this one I'll just kind of look it over, but a lot of what goes on here is the same as what we just went over. So if we see it says at time t, the position of the particle moving in the xy plane is given by the parametric functions. And again, just like the last couple, well, at least the first one, we are given our dx dt, and that's actually all they give us. And then they say the graph of y consisting of 3 line segments is shown over here. So this is actually, we're going to be using our graph to find like the y of t and different things like that. So let's see. At time equals 0, the particle is at position 5, 1. All right, so that's going to be important to know. All right, so it says find the position of the particle at t equals 3. Okay. So let's see. We have our r. Let me use a different color here. Vector r of our new position 3 equals our old position at 0, so r of 0, plus our displacement, so that'd be 0 to 3 of our velocity. So let's see, we have our position is 5, 1, and then we have integral from 0 to 3 of dx dt, so we're given that, sine of 3t squared, is that dt, comma, from 0 to 3, and this is going to be y prime of t dt. Now remember, we're not given dy dt, but we are given the graph, and so we're going to be using that along with FTC, our fundamental theorem of calculus. So we have, I can actually write this as 5 plus, and then I'm going to go ahead and calculate that integral. So that'd be 0 to 3, and then that would be x squared plus sine of, oh, don't need that, 3x squared. Close that out, so that should be good, and then we just integrate that. Okay, there we go. So that's going to be 5 plus 9.377, comma. Now for this one, we have the 1 plus, and then this is going to be, think FTC, fundamental theorem of calculus. I have y prime here. So that's going to be y of 3 minus y of 0, top minus the bottom. Okay? So this is the graph of y. So I just go and pull out those values. So y of 3 is going to be negative 1/2. Y of 0 is going to be 1. So this was, what did we say? This was 1/2. This is going to be 1. So then we can go ahead and find we need. So the first one, just going to go ahead and add 5. and we get 14.7 or 377, comma, and then that's going to be 1 plus 1, let's see, 0.5, and then minus 1, so it should come out as just 0.5, so 0.5, and that should be our new position. All right. Oh, one tiny mistake that I made here. So sorry, that was negative 1/2, and so then that would be negative 1/2 there. All right. So there we go. Let's see. So we have find the slope of the line tangent to the path of the particle at t equals 3. So remember, we have now two types of derivatives. We have the derivative of the vector, and we have the derivative of our parametric equations. And for this one, we want to find the slope of the tangent line. So we're going to have to use our parametric derivative. So that's going to be dy dt over dx dt. So dy dt, we're going to pull from the graph. So we're going to go ahead and do dy dt at t equals 3. And so for the bottom, we're going to go ahead and pull, I'll go ahead and get that in a little bit. So dy dt, and then for the bottom, we're going to use what they gave us, the t squared plus sine of 3t squared. So to find our dy dx at t equals 3, so for the top, dy dt, we're just again going to pull from our graph. Now at 3, our slope of our line is positive 1/2. So that's going to be 1/2 for the top. On the bottom, we're going to have to use our calculator. Oh, I don't need the integral. I was about to throw it into the integral. I don't need that because I already have the derivative. That is dx dt right here. So I can just go ahead and throw 3 into that. So that's going to be 3 squared plus sine of 3 times 3 squared. And that should give me 9.956. We go ahead and divide that, so 0.5 divided by our answer there, and we get the slope of the line should be 0.50. Oh, let me rewrite that. I wrote that incorrectly. 0.050. Okay. All right. Now we want to know the speed of the particle at t equals 3. So remember, speed is going to be the integral from, let's see, speed of the particle at 3. So, oh, never mind. I was about to do total distance. Go back up here. Speed is the magnitude. So I was about to throw it into the total distance. I don't need that. So that's just going to be the magnitude of our velocity vector at 3. So that's going to be square root of, and again, our dx dt at 3, so that'll be 3 squared plus sine of 3t squared, plus, and then again, that'll be our dy dt at 3, which was 1/2 squared. So we already know those two values. So again, remember that was our x prime of t squared and y prime of t squared there. And so x prime we already knew, y prime we pulled from the graph. Okay? So let's go ahead and throw that in. So we already have the 1 value, so that's the 9.956 squared plus the 1/2 squared. So we just need to throw that all into the calculator. So let's see if I can maybe store that. Oh, no, I should be able to just recall it there, but I'm just going to go ahead and store it into A, just so I have that. It makes my life a little bit easier. So I'm going to go square root, and then that's going to be just that A squared. And then I want 0.5 squared, so plus 0.5 squared. And that should give me 9.969. There we go. All right, one more. Find the total distance. Okay, so this is where I was about to do on this one. So total distance. Oh, I wanted green on this one. So total distance. That is what I was about to do on the other one. So that is the integral from 0 to 2. So 0 to 2 of our magnitude dt. So that's going to be the integral from 0 to 2 of the square root. So remember, this is our what's I about to say? Total distance. This is our arc length that we want to do. So we have 0 to 2. 0 to 2. Wonder if I'm going to have to split that up. Okay. So I'm looking up again at the graph here, and since I have two different slopes here for our function of y, I'm going to have to split this up between from 0 to 1 and then 1 to 2, with the two different slopes right here being -2 for dy dx, and then this one is a slope of 0. So I'm going to have to split this up into two parts, because I know this is going to be x prime of t squared plus y prime of t squared dt. But again, since this has two different slopes from those two parts, we're going to go ahead and split this into two parts. So this is going to be the integral from 0 to 1 of our, so this would be the square root of x prime of t squared plus, and then the slope between 0 and 1 was -2 squared for the y, plus the integral from 0 to 1, square root of x prime of t squared. And then for this part, oh, I forgot, I still did 0, 1. That should be from 1 to 2. And then that would be 0 squared, because our slope for the y component is 0. So we're going to go ahead and throw all that in. Since I'm going to be using them both here, I'm going to go ahead and just put in that this dx dt, or x prime. I'm just going to go ahead and put that in here into y1, so I can just recall it when needed. So x squared plus sine of 3x squared, not 3. Okay, x squared plus sine of 3x squared, right? That's what I have. Okay, so that's y1. All right, so let's go back down here and plug everything in. So with my two integrals, so that should be from 0 to 1, and then that's going to be the square root. And again, I'm just going to do my y1, So y1 squared plus -2 squared dx. So that gives me 2.238 plus, and then we can do that one, the integral from 1 to 2. And that will be the square root, again, of y1 squared plus 0 squared dx. So that is 2.112. So I'm going to go ahead and add that to that value there and get our total distance for all the way from 0 to 2 as 4.349, truncating that. All right. So there we go. Seeing all those different type of problems using these motion formulas that we have. Again, very similar to our motion problems that we had earlier. All right. Well, hopefully that was helpful, and have a fantastic day, everybody.